My name is Maria Esther Vidal. I'm from the University Simón Bolívar in Venezuela. And with Maribel Acosta, I'm going to present you the challenge to be addressed during benchmarking SPARQL federated engines. And our objective is to be able to differentiate between the green apples and the red apples. So let's see the agenda today. First, we will start with the parameters that may impact on the performance of federated query engines. Then I will show you an example of benchmarking SPARQL federated engines with the existing benchmark. Then Maribel will present a formalization, a formal framework that we have to understand the complexity of existing SPARQL queries. And finally, we will present our lesson learned. So to start with the presentation, let's see what is a federated query engine. So we have public available SPARQL endpoints, and the idea with a federated SPARQL query engine is that this is a client-server architecture that is able to answer queries based on the data exposed by these services. And these services are able to access linked data, RDF data from the link Open Data Cloud. So which are the existing SPARQL federated query engines? Well, we have FedEx, ANASIP, Splendid, Avalanche, RQ, and SPARQL QPD. So what is the architecture? The architecture is a typical architecture of a query engine, but we have a source selection and a query decomposition component. And this is in charge of using information about the source descriptions, and in this case, the source descriptions are information about the endpoints, the SPARQL endpoints, and this component is able to decompose the query into subqueries, and these subqueries should be evaluable for the SPARQL endpoints. So we have a query optimizer, also a physical optimizer, and a query executor. So let's see what are the parameters that may impact on the performance of these engines. So we have query dimension, data dimension, platform dimension, and source dimension. So I will show different examples where all these engines can be impacted. And where are the dependent variables? So source selection time, we want to see how source selection time is impacted by all these parameters that I will explain to you, the execution time, and also the answer completeness. So this is one of the benchmarks that is available in the community. This is FedBench. And FedBench is comprised of all these real-world data sets. So we have Wikipedia, New York Times, Link, MBD, Jamengo, Unamis, and all the rest of these collections. And also, we have all these queries. We have queries from different domains, cross-domain, life science, and linked data. And we have, well, for the cross-domain, we have 7 queries. For the life science also, we have 7 queries. And for the linked data, we have 11 queries. And let's see when we talk about query dimension. And when we talk about query dimension, what we are talking about is all the parameters from the query dimension perspective that could impact on all the tasks that a query engine have to perform. So for example, when we talk about the query shape, we will be talking about star shape queries or chain queries. And when we talk about these type of queries, definitely the shape of a query will impact on the source selection time, the execution time, and the answer completeness. The number of triple patterns will also impact on these 3 tasks. And also the number of general predicates. So I will give you an example of the type of queries that I'm thinking about. So suppose I want to get the information about the KEK component identifier or of a particular type of drugs. These are the drugs that I'm thinking about. So in SPARQL, this is the type of queries I will write. So I say, okay, I want the information about the KEK component ID, but I want to say that the information that I'm related to that particular drug is of one particular type. And the RDF type is a general predicate. So in this query, I only have one triple pattern that is bound to a general predicate. In the second query, I want to get that type of drugs, but also I want to get the equivalent drugs in different data sets. So in this case, I have all same as, and here I have two triple patterns bound to general predicates. Here I have 3, and here I have 4. But what is the idea? The idea is that we evaluated these 4 queries against this federation of endpoints, and this federation of endpoints are from FedBench. And see what happened. We use all these query engines. These are the state-of-the-art query engines, and these are the 4 queries that I mentioned. And when we started to evaluate, this is the throughput. And see what happened. In all the cases, the performance of the engines decreases as the complexity of the queries increases. And what happened? What happened is that for each of these predicates that we have bound to general predicates, we have all these sources that are able to answer that particular predicate. The same happened with query 1, query 2, and query 3. So this is one of the parameters that have to be considered when one defines a benchmark, but unfortunately, in the existing benchmarks, this is not considered. Another parameter is the ones that belong to the data dimension. And in the data dimension, we have to consider how the size of the data set, the data fragmentation distribution, the type of partitioning, and the data, how the data is distributed in the endpoint. So let's see this example. We have data fragmentation, and we divided one data set in 3 fragments, and the intersection between these 3 fragments is empty. Then we did horizontal fragmentation, where we have 3 fragments, but the intersection is not empty. So in some cases, we have some triples that were repeated along the fragments, and for one particular predicate will appear in different fragments. And finally, we have vertical fragmentation. And in vertical fragmentation, each fragment contains all the triples of a particular predicate. So we created like 4 different configurations. The first one, vertical partitioning without replication. What we have here is 3 fragments, but we don't have replication. We have the vertical partition, but we don't have replication. Vertical partitioning with replication, where we have 3 fragments too, but we replicate the data. With horizontal partitioning without replication, we had 2 fragments, but we didn't replicate the data. And finally, with horizontal partitioning with replication, we have 2 fragments, but we replicated the data. So what is the results of running experiments against these 4 configurations? So suppose we have one endpoint with all the data, and we consider only FedEx and ASIP. So in this case, the 2 engines exhibit similar performance. So we will say that the 2 engines are equally the same. But when we go for vertical partitioning without replication, we see that an ASIP is more expensive than the other engine in terms of course, expensive in terms of execution time. But if I consider horizontal partitioning without replication, FedEx is more expensive than an ASIP. And vertical partitioning with replication, an ASIP more expensive than FedEx. And finally, horizontal partitioning with replication, an ASIP is cheaper than FedEx. So suppose I'm writing a paper, and I want to show my green apples. So I will just pick the green apples that are showing that my engine is the best. Why? Because in the benchmark, nothing is specified with respect to the type of fragmentation that I have to have when running the experiments. So this is definitely a limitation of this existing benchmark. On the other side, if we consider the data distribution, suppose I have one single endpoint, and in this single endpoint, I have all the data. So in this case, clearly, an ASIP outperforms FedEx. But in the other way around, we will have less clear performance. So it's clear that the platform also impacts on the execution of all these engines. And finally, the source dimension. If we have different type of endpoints, for example, we have delays, initial delays, or latency in the network. So we set up an experiment where we have perfect network, fast network, medium fast network, medium slow network, and slow networks. And see what happens, similar performance that we observed before. In perfect network, in some cases, an ASIP win, in the other FedEx win, and the same. We can interchange the performance of one and the performance of the other. And the idea is that because this is not specified in the benchmark, I could choose the one that is convenient for me. So let's see an experiment that we perform for testing how good is this benchmark with respect to the complexity of the queries. So we set up a federation with the 25 queries from the benchmark, from FedBench, and we also defined 11 additional queries. And these queries were completely different to the queries that were in the benchmark. Actually, had more triple patterns, and also we could decompose these queries into subqueries that were star-shaped queries. So the shape of a query was completely different to the one in the benchmark. Also, we set up 10 endpoints, and we call this federated federation. And also, we set up an endpoint with all the data. One endpoint with, and we call this the complete federation. And we define 6 configurations. In configuration 1, we have an ASIP with a complete distribution of the data. In the configuration 2, we have an ASIP with a federated distribution of the data. Remember that the complete distribution is all the data inside one endpoint. The federated is the data in 10 different endpoints. RQ, complete distribution, RQ, federated distribution, a configuration 5, FedEx, complete distribution, and configuration 6, FedEx, federated distribution. And we compute the Spearman-Rho correlation because we wanted to see the correlation between the performance of all these configurations. So for computing the Spearman-Rho, we order for each of the type of queries in this benchmark, we order in a list the queries based on the execution time spent by the engine when these queries were run. So for example, in this case, we say CD1 is the first one because the execution time, okay, we order this. And we have C2 is the one with the less execution time, C1 is the second, C5, C6, C7, 4, and 3. And for each configuration, we compute the Spearman-Rho correlation. And the Spearman-Rho correlation, suppose between configuration 1 and configuration 1 is 1 because these orders are exactly the same. So for example, if we have 2 lists and the lists are exactly the same, the Spearman-Rho correlation is 1. On the other hand, if we have a Spearman-Rho correlation minus 1, we have that one list is the opposite of the other one. And we have a high correlation when the lists are quite similar. So what we evaluated? So what we evaluated is that for each of these queries in the benchmark, we try to see the correlation between these configurations. So for example, here we have the 6 configuration. Remember, configuration 1 is an ASIP complete distribution. configuration 2 is an ACID federation distribution, and so on. And we compare the orders of the queries, and we compute the Spearman row. So the diagonal of this matrix is the correlation 1. Why? Because when I compare one configuration with respect to that one, the correlation is 1 because the two lists are the same. But when I have a positive correlation, I draw that with a blue circle. And see how many blue circles I'm seeing in this picture. So my only two red apples are these when I say that I compare an ACID federated distribution and RQ complete distribution, because they exhibit opposite performance. But when I compare an ACID federated distribution with FedEx federated distribution, you will see that they exhibit positive correlation. So I'm going to the other group of queries that is offered in this benchmark, and I see a similar performance. See, again, an ACID federated distribution and FedEx complete distribution exhibit an opposite performance, but the same correlation that I observed before. An ACID and FedEx federated distribution exhibit positive correlation. And finally, with the life science domain in this benchmark, I could say exactly the same. An ACID and FedEx exhibit the same, a positive correlated performance. So I will say, okay, when I compare FedEx and an ACID, they perform equally the same. But suppose I define more complex queries. And when I define more complex queries, I'm able to uncover these red apples. And these red apples were there hidden, but I have to, in some way, discover them. And see, if you see this experiment, here what we are observing is that an ACID and FedEx federated distribution exhibit an opposite performance. And we couldn't observe that before. Why? Because we were considering very, very simple queries. So what is the message? The message is that with this type of benchmarks, you have to consider many different parameters in order to exhibit and to study the different properties of, in this case, the engines that we want to study. So right now, Maribel will present a formal framework that we have defined in order to analyze the performance of these engines.
Thank you. So as Maria Esther said, she already, the microphone. Yeah. I don't have pockets. Thank you. Thank you. Okay, so Maria Esther provided like the experimental study that we have performed on this FedBench benchmark. Now I'm going to talk about formalization. So how, from a theoretical point of view, we can actually analyze the complexity of the tests that we are actually running on these queries. So we started from a point, and in this case, I'm going to present a formalization of the query decomposition problem. And as Maria Esther said before, this component is the one that actually builds the subqueries that are going to be posed against the endpoint. So this actually have an impact on the performance of the queries. So let's start. This is not working. No. Okay. Okay, so the motivation, so we started studying the query decomposition problem, casting it into the vertex coloring problem. And so we have the SPARQL queries, and we map them into a special graph that we call the vertex coloring graph. And this allows us to determine the complexity of the benchmark queries, and this will allow us also to explain the observed behavior that we are actually seeing with experiments that Maria Esther just showed us. So let me introduce the vertex coloring problem. is the problem consists on coloring the vertices of a graph such that no two adjacent vertices share the same color. So I have this graph here with the nodes A, B, C, and D, and since A and B have a connection, have an edge between them, I cannot have them in the same color. So A is of one color, in this case purple, and B is in a different color. Also, one restriction on the vertex coloring graph is that we have to minimize the number of colors that we use for a given graph. So actually, this example that I just presented here is the optimal solution for this graph. So for this particular graph, I can only use 2 different colors. And this problem has shown to be NP hard, but the good news is that there is a solution called Dissatour, which is an approximation that is implemented with a greedy algorithm that provides an optimal solution to the vertex coloring problem and with a certain restriction. So it depends on the shape of the input. So Dissatour is able to find an optimal solution in polynomial time for graphs with the following shape. So with the shape of a cycle, the shape of a wheel, star-shaped graphs, and the other graphs. Also for the disconnected graph, of course. So how do we map our query composition problem into this problem? So we are going to draw nodes in the vertex coloring graph, and these nodes correspond to the triple patterns that we have in the original SPARQL query. And we're going to add edges to those nodes only if it is not possible to perform a join between the 2 triples, so we don't allow Cartesian products in a single star, and also the triple patterns that cannot be answered by the same endpoint are going to be connected by an edge. So let me show you an example, and this is the query 6 from CD in FedBench, and it's a query about Germany, and it's composed of 4 triple patterns, and we already have performed the source selection. So T1 is going to be answered by the endpoints Jamendo, Semantic Web Dogfood, DBpedia, and Bibliographic. Triple pattern 2 by LMDB, etc., etc. So this query have many different ways to be decomposed into, but I'm just going to show you here 2 possible query compositions. One is I'm going to run a query with the star about the artist, and then I'm going to join with another star, the 3rd triple pattern, and then I'm going to join that, and then the result, I will join them with the 4th triple pattern. That is one way to do it. Another way to do it is just to take the first 2 triple patterns into star, and then join them with the stars of the 3rd and the 4th triple pattern. So which decomposition do we want? Well, we actually take the SPARQL query, and then we're going to map it into the vertex coloring graph. So as I said before, for each triple pattern, I create one node, T1, T2, T3, and T4, and then I'm going to add the edges, which are the restrictions on the graph. So I'm going to add an edge between T1 and T3 because they don't share a variable. So if I share them, if I join them, they will actually produce a Cartesian product, and I don't want that. That's why I put an edge between them. And also I do the same between T1 and T4. And when I go to the next node, T2, I also add a node between T2 and T3 and T2 and T4, and that's it. So this is the vertex coloring graph for the SPARQL query of FedBench. So when we have this, we could actually run Dissatour to find the number of colors that I can put in this graph. And as I showed you before, I can put 2 colors in this graph. And what this actually represents is the following decomposition. So the first 2 triple patterns will be joined on a single star, and then T3 and T4 will be joined, these 2 stars, in a single subquery against these sources. So now let's imagine that I have 2 queries and I want to test them, or I want to analyze them from a theoretical point of view. So I have query 1 from FedBench. I will call it query 1. And I have query 2, which we have defined as one of our complex queries composed of 48 triple patterns. And actually, this is not very complex since we have evidence and references in which real applications can actually build SPARQL queries with more than 50 triple patterns or even 200 patterns in the case for the medicine domain. So we can analyze this using the vertex coloring graph, and you can see here the number of sources that can be answered, the number of sources that can answer a certain triple pattern, and the number of sources that can answer all these triple patterns. So what is affecting here actually is not the number of sources, but the number of comparisons that I have to do in order to identify the sources. So here I have 48 triple patterns that I have to check against all my federation in order to identify the sources. So this is actually an indicator that this type of queries might impact my query engine. Now, if we take a look at the vertex coloring graphs, this is exactly the same graph that I showed before. And as you can see, it's quite simple. It's composed of only 4 nodes. But the graph for the second query is actually very dense. It's highly connected because I have many, many restrictions. And these restrictions correspond to Cartesian products that I need to avoid in order to compose the subqueries. And then finally, when I take a look at the decompositions, query 1 is just for the triple patterns. There are no restrictions, while the number of possible decompositions with exclusive groups is really, really high. So this will also affect the query execution. And if we take a look at the type of decomposition that an APSI performs, we can see that it is actually slower, the space of the compositions, but it still is much, much more complex than when we take a look at query 1. So in the conclusions from this example, we can say that query 1 is simple or very easy to solve. Actually, I can find a decomposition with this Satur in polynomial time for this query, while for the second query, I would say that it's very difficult because it's very hard to find all the sources and all the possible decompositions for the second one. So what happened with FedBench? Well, we did this analysis for all the queries of FedBench, and then we realized that they are actually very, very simple. So in the first query for the cross-domain collection, we see that the vertex coloring graph is actually disconnected, so I can find a solution in polynomial time. The same for the second one, the same for the third one, and so on and so forth. So for the cross-domain, they are actually all very simple. They are disconnected bipartite or tripartite graph, so I can find a solution. And if we take a look at the other collections, in the case of linked data, it's the same. There is no variation. All of them are disconnected, bipartite or tripartite, and the same with life science data. So the conclusions from this is that actually FedBench is not really stressing our engines. But when we take a look at the complex queries that we have defined, we can see that the shapes of the vertex coloring graph are more diverse. And actually, we have 7-partite graph and 9-partite graph. And when we try to run these queries with the existing engines, say an APSI and FedEx, these queries took longer than 30 minutes. So this is not actually like a problem of the platform, but this means that these engines are not right now capable of running this type of queries. But this is not contemplated in the current FedBench benchmark. So other visualizations that I have shown you are available in this tool online called Silurian. And what are the lessons learned? Well, we have run extensively experiments. The first one is that test beds should provide the mechanisms to test, and I would like to emphasize, to stress the engines in order to, in the different dimensions so that I can actually say that my solution is robust enough. So the second lesson learned, I would say that is that the test bed should provide not only the data sets and the test, but also the values of the different parameters. Why? Well, because this will allow for reproducibility of the experiments. So if you run some experiments, I can actually rerun them under the same conditions. The generality of the results, so I can say, oh, this engine is able to run for most of the queries, not for only a couple of queries that you design in your benchmark. And finally, for avoiding hiding the red apples. So when we have a very specific set of tests, we can actually not hide the configurations in which our engines don't win. The third lesson learned is that the formalization of the different problems is very important. Here we just have provided for the query decomposition problem, but there are many other problems in federated scenarios. And this will allow us to understand the properties of the test and also to understand the impact of the observed variables. And finally, the fourth lesson learned is that we have to include challenging tests in the test beds. So this is the only way that we can identify open problems, and this is the only way that we can push progress in our technologies. So in summary, we have studied different parameters that may affect the behavior of the federated SPARQL engines. We have the query dimension, data dimension, platform, and source. We have evaluated existing federated engines. We show you the studies of the Spearman correlation. And finally, we have studied the complexity of the FedBench queries using the formalization of the vertex coloring graph. For our future work, we plan to extend existing benchmarks to consider all the parameters that we just showed you in this presentation. Some of the references. Thank you.
Questions or comments? No questions. No. Okay, I have a question for now. So you look so doubtful. So are people using federated SPARQL engines right now in real deployments?
Not too much.
Not too much.
Well, we have users. We implemented an ASIP, and we have at least 5 or 6 users.
Mm-hmm.
So I don't know if they are using that in a real-world scenario, but I think they are.
That's for 2 reasons. Not that they don't like to. I remember, I know some people that were optimizing their federation plans out of Germany, but they never got this far. I haven't seen anything that's about as comprehensive as what we currently see. And most of these guys that do it in Europe don't look that attractive.
Now, what I do like the form analysis. It shows that kind of we call these choke points. So it appears that the structure of the underlying structure of the graphs, the dependency graphs, is strongly affecting the complexity of this problem.
Yeah. Well, it's bad enough to do it local. And the federation is, significantly harder. But there's some people, we hardly have users who do federation. And, some people would like to do federation. We advise against doing federation because it's too difficult. But evidently there's, it very much depends on what one is after. But it's very interesting work, must say, yeah.
Yeah.
But in the rest of the
I
time,
really want to get it to the relevant people back in Sofia to dig into it.
right?
I mean,
Thanks.
it was border edge to me to what I can follow in this type of presentation because it's complex stuff, but looks very promising. So,
Any other questions?
are you coming out of South America to make this presentation, or you're just coming from Germany this time?
Well, I'm in my sabbatical leave in Germany, and she is in her PhD in Germany.
In Karlsruhe.
Okay. Okay. Thanks.
Thank you.
Thank you.
The floor to Amelia.